Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject, up to now, we have seen various topics. We have discussed about stresses and types of stresses and types of strains, and then what is the relation between stress and strain. And also we have discussed about elastic constants and shear stresses, shear force and bending moment diagrams. And then in previous session we have discussed about bending stresses. So in these bending stresses we have derived the bending equation, and we have learned the theory of simple bending. But today's session, so I want to explain about the position of neutral axis and moment of inertia. And then we will see the bending stresses in unsymmetrical beams. So that is, so last one, first we will discuss about the neutral axis. Why? Because the position of neutral axis plays important role in bending stresses. And the moment of inertia also, how to calculate the moment of inertia for different sections, we will see. So before going to enter the main topic, the student should know about course outcome. The course outcome, the end of the course, the student should be able to analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. So at the end of this topic, the student can explain about theory of simple bending, and also he can analyze the theory of simple bending for illustrating the distribution of bending stresses. Whenever the beam is subjected to various loads, how it will react, the beam, how it will respond, they can analyze. So what are the bending stresses and beams? So once recall the previous session, the bending stresses, the bending moments and shearing forces are set up at all sections of a beam. When it is loaded with some external loads, as a matter of fact, the bending moment at a section tends to bend or deflect the beam, and the internal stresses resist its bending. So whenever the beam is loaded with some external loads and movements, so what will happen? That particular section, the section of a beam tends to bend or deflect the beam. So the process of bending stops when every cross section sets off full resistance to the bending moment. So the resistance offered by the internal stresses to the bending is called bending stress. And the relevant theory is called the theory of simple bending. The resistance offered by the internal stresses to the bending, that is called as bending stress. Note down, this bending stress is the combined effect of both tensile and compressive stresses. So already I told you. So whenever the beam is subjected to loading, sometimes that is depends upon the type of loading and movements. Top portion, top layer undergone compression and bottom layer undergo tension. Sometimes vice versa. See, in this bending in beams, the before deformation, there is no disturbance in their straight lines and vertical lines. But after deformation, after subjected to loading, so your movements, the horizontal lines becomes a curve and the vertical lines remain straight. Clear? So after deformation, so it means some deformation will be occurred in this beam. It may be at the top and bottom. But at the center of the beam, there is no change. There is no deformation. I will show you the diagram. See, the bending, after loading, the bending is like this. So, some curvature. So the horizontal lines are converted into curved lines. Before bending, the lines are like this. There is a uniform distribution of lines, uniform distribution of forces. See, whenever this beam is subjected to some loading here, point load, moment, that is couple, and point load, and UDL. So the load acting at this beam, so due to this load, some deformation will be occur. The top layer so undergone compression, the bottom layer tension. See, in this beam, so here one end is fixed, other end free, and some loads, the point loads are acting with some distance. So the after loading, the beam is bends like this. So it means that top portion, top line is undergone tension, and the inside bottom one is compression. See, in this, the location of neutral axis. So here, the center one, suppose the beam is like this, the center line passes through the beam, that is called as neutral axis. Why it is neutral? When it's subjected to loading, so there is no change in their dimension. So that is called as neutral axis or neutral layer. Neutral layer. So here see the position of neutral axis, the line of intersection of the neutral layer with any transverse cross section of a beam is known as neutral axis of that section. So we have seen that on one side of the neutral axis there are compressive stresses. So whereas on the other there are tensile stresses. So at the neutral axis there is no stress of any kind. So at this neutral axis, already we have seen there are compressive stresses one side and other side is tensile stresses. So at this neutral layer, neutral axis, there is no stress of any kind. So how to fix this position of neutral axis for a particular beam? See here, consider a section of beam as shown in figure. Let NA be the neutral axis of the section. Take a small elemental section, that is PQ. So consider a small layer. The small layer is PQ. So the distance, the layer distance PQ of the beam section at a distance y from its neutral axis. So as shown in the figure. Take let here the small elemental area delta A is the area of the layer PQ. See here, consider a section of a beam and then neutral NA be the neutral axis of the beam section, and also consider a small section with wide distance from where? From neutral axis. Now the let delta A is area of the layer PQ. Now the intensity of stress at a density distance y, that is stress. So from the bending stress equation, already we have derived in the previous session, the bending stress equation, sigma by y is equal to E by R. So here the intensity of the stress is sigma is y into E by R. Y into E by R. So E and R are both are constants. E is the elastic constant, Young's modulus, and R is the radius of the curvature. So now the force on the layer. How do you calculate the force on the layer? Stress on layer multiplied with the area of layer. Already you know the stress is equal to 4 load per area. But here the force is on the layer P and area of layer. So area of layer already you have taken delta A. The stress is y into E by R. So substitute this sigma value here, y into E by R into delta A. So the sigma value substitute in this, and the delta A is the area of the layer. But we know the moment of any area about an axis through its centroid is also equal to 0. So as neutral axis coincides with the centroidal axis, thus the centroidal axis of a section gives the position of neutral axis. So here E and R are constants. Moment of any area about an axis passing through centroid is equal to 0. So the force on the layer y into E by R into delta A. Now you may calculate the total force on the layer. The total force on the layer, that is total force on the layer need to calculate total force on the layer. So how do you calculate the total force on the layer? So total force on the layer. You know the individual force on the layer is E by R, y into E by R into delta A, y into E by R into delta A. So integrate, you will get total force. So integrate. So now you can write after integration So after integration in total force, integrate y into E by R into. So take outside E by R, delta integral y into integral y into delta. So the E and R are constants. We know the movement of any area about an axis passing through its centroid is equal to g. So you may write the y into delta A is equal to g. So it means the neutral axis coincides with the centroidal axis. So suppose one section is there here, the beam section. This is centroid. So the, the neutral axis coincides with the centroidal axis. That is y. The distance is y. So this is the position of neutral axis. The central axis of a section gives the position of the neutral axis. Suppose for this triangle section, the center of gravity is here. So at the center of gravity coincides the neutral axis. Now to take the neutral axis at their section centroidal axis. So that is the position of the neutral axis. So now we will discuss about the moment of resistance. See, so what is this moment of resistance? So on one side of the neutral axis there are compressive stresses, and on the other there are tensile stresses. One is compressive stress and another one is tensile stress. So these stresses form a couple. So whose movement must be equal to the external movement. So the moment of this couple which resists the external bending moment is known as moment of resistance. The moment of this couple which resists the external bending moment. See, here suppose one beam. So like this the moments are acting. So these the compressive stress or tensile stress form a couple which resists the external bending moment. So that is known as moment of resistance. So here how do you calculate the moment of resistance? So consider a section of a beam. So like in the previous position of neutral axis beam. So let's take neutral NA be the neutral axis of the section. Already you know. Now consider a small layer, that is PQ, of the beam section at a distance y from the neutral axis. The small layer PQ of the beam section at a distance y from the neutral axis as shown in figure. So let the delta A is area of the layer PQ. We know that the intensity of stress at a distance y is equal to sigma is equal to y into E by R. So already we have seen in the previous in first slide, starting the slide. Now the force on the layer, stress on the layer and area of the layer, this one also we have seen, sigma into delta A, y into E by R into delta A. See, so now take, let M is equal to moment in Newton member. I is the moment of inertia in millimeter to the power 4, mm to the power of 4. The sigma is a bending stress in Newton per mm square. The y is distance of a section from neutral axis in mm, and E is Young's modulus in Newton per mm square. R is the radius of curvature. So now, the equation, the stress sigma will be maximum when y is maximum. Hence, the above equation can be written as m is equal to sigma max into I by y. So you can write I by y is z. Z is here section modulus. So I will explain here later the section modulus. The stress will be maximum when y is maximum. Okay? So here the sigma is equal to y into E by R into delta A. So from this equation or bending stress equation, sigma by y is equal to E by R. You can write the equation. So like this. So M moment is equal to sigma max into Z. So what is Z here? Z is the section modulus. Where is section to section? So I is the moment of inertia. For rectangular section, we know that the moment of inertia of a rectangular section, so about an axis through its center of gravity. So section modulus of various sections, first you see the rectangular section. If you take a rectangular section like this, so the neutral axis that is passing through center of gravity. We know that the moment of inertia of rectangular section about an axis through its center of gravity, the I is equal to BD cubic 1. So what is B and D? The B is the breadth of the section and the depth or height of the section. So that is D. For this rectangular section, the moment of inertia is BD cubic 1. So modulus of section Z is, Z already you know, Z is equal to I by Y. I by Y. So where I is BD cubic 1, the Y is the distance of the cross section from its neutral axis. So here the center of gravity axis and the neutral axis coincides. So the distance is, that is y. So what is the distance here? D by 2, half of the depth of the height of the section, D by 2. Now substitute in place of y in this, the BD q by 12 divided by y, that is 2 by d. So BD square, so finally we will get BD square by 6. Why? Because the y is equal to d by 2. For hollow rectangular section, so for a hollow rectangular section, the I is equal to BD cube by 12 minus small BD cube by 12. So inside dimensions B and D, breadth and depth, the outside dimensions are capital B and capital. So neutral axis passing through the center. So here for smaller dimension, that is the depth is y is equal to d by 2. For bigger one, that is outside portion, that is capital D by 2 already given here. The y max, the maximum distance is capital D by 2. For hollow rectangular section, so write down the equation, the moment of inertia, BD cube by 12 minus small BD cube. So now the Z is equal to, so write down I by Y. So Z is equal to I by Y. I is equal to BD cube by 12 minus small BD cube by 12. Divided by Y. The Y is the Y maximum. The Y maximum you take, that is D by 2. Clear? So here, after simplification, write down this equation now, like this. The Z is equal to 1 by 6D into BD cube minus small BD cube. So these B and D are the dimensions of the section. Clear? So next, hollow circular section. So take the hollow circular section. So that is I is equal to 5 by 64 into d to the power of 4 minus small d to the power of 4. For circular, only solid circular. So suppose you take the solid circular one. Clear? So the center of gravity, the dimension is the diameter d. So now for this, the I is equal to 5 by 64 d to the power of 4. This is not hollow. For hollow one, the inside dimension also there, that is d by small d and capital D, external diameter and internal diameter. The internal, suppose the beam is like this. So inside diameter is d and outside diameter is capital D. Inside one is small d. So the Z is equal to 5 by 32D into d to the power of 4 minus small d to the power of 4. So after simplification, Z is equal to I by Y. I already given 5 by 64 into d to the 4 minus small d to the power of 4. Divided by Y. Y is equal to capital D by 2. Clear? So now write down, simplify, and you will get Z, that is section modulus. 5 by 32D into d to the 4 minus small d to the power of 4. Clear? So like this, how to write the section modulus and moment of inertia values for various sections. So in this session, we have learned the moment of resistance and then position of neutral axis. So how to fix this position of neutral axis and how to calculate the moment of resistance for various sections, section modulus formulas also we have seen. So for this PPT, so I have taken references S. Ramamurthan, that is Strength of Materials. The title of the book is Strength of Material, and publishers are Dundigal. So another book, that is R.K. Rajput. The title of the book is Strength of Materials. Publishers are Sun and Co. R.K. Bansal, a textbook of Strength of Materials. Title of the book is, author name is R.K. Bansal. The publishers are Lakshmi Publications. And one more is Horace Kurmi and Gupta, The Strength of Materials. S and Co, the publishers. So these are the references I have taken for this PPT. Thank you.
Like, share and subscribe. hit the bell icon for more updates.